In this video, we are going to continue our discussion on molecular polarity. So last time we saw that a molecule can be polar or nonpolar depending on its individual bonds and whether they're polar or nonpolar, and the shape of the molecule. So in general, a molecule is nonpolar if all of its bonds are nonpolar. So for example, we've seen the H2 molecule previously where we have two hydrogen atoms bonded together and they're sharing electrons. And because we have the same atoms bonded together, they have the same electronegativity values. So the difference in electronegativity is 0, which means the bond is nonpolar, but additionally the molecule as a whole is nonpolar. And that will be true for molecules that have more than two atoms. If all of the bonds are nonpolar, then the molecule is nonpolar. And then down below, in general, a molecule is polar if it contains polar bonds, except when the bond polarities cancel each other. So if the polar bonds in your molecule do not cancel each other, then the molecule is polar. But we saw, for example, CO2, and even though the individual bonds were polar, they canceled each other out because the molecule is symmetrical and the atoms are evenly spaced around the central atom. So the oxygen atoms are evenly spaced. So we actually call these arrows dipoles. And dipoles or dipole moments can tell us where electrons are moving. So in this case, oxygen is more electronegative. It likes electrons more. So we do have an overall movement of electrons more towards oxygen. However, the molecule's overall dipole is 0 or none because those individual dipoles for each carbon-oxygen bond cancel each other out. And again, that's due to the shape of the molecule. Now, water, however, water has individual dipoles for each oxygen-hydrogen bond, but they don't cancel each other in this case because they're pointing overall up towards oxygen. So they are not equally spaced around that oxygen. So this molecule has an overall dipole pointing up towards oxygen, which makes it a polar molecule. So let's look at some other examples. So on the right, I have a BF3 molecule. Oh, and there's a typo here. This should be BF3, not BH3. So this is a trigonal planar molecule because we have boron in the middle and it has 3 bonded atoms and 0 lone pairs. So in the chart that we saw in the last video, this would fall under the trigonal planar geometry. Now remember, previously we did see this shape and we said that the atoms in a trigonal planar molecule are all 120 degrees apart. So those fluorines are equally spaced around boron. So if we were to look up the boron-fluorine electronegativities, we would find that fluorine really likes electrons compared to boron. So electrons in this molecule are going to hang out with fluorine more often than boron. But because those individual bonds are equally spaced, even though they're polar, they're going to cancel each other out. So the overall molecule is non-polar. So again, I like to think of this like tug of war. So in this case, we would have three ropes that are all connected in the middle. Now, if we have three teams that are each tugging on one of those ropes, and they are all tugging with equal force, then no one's going to move in a particular direction, and no one wins. So it's the same thing here. We have three equal forces that are all pulling in equally spaced directions, so they cancel each other out. However, let's look at NH3 down below. So NH3 does have a lone pair on top of that nitrogen. So that means nitrogen has three bonded atoms and one lone pair of electrons. So it has four total things around it, and one of those is a lone pair. So according to the chart that we saw in the last video, this molecule has a trigonal pyramidal shape, or it's a trigonal pyramid. Now, if we were to look up the nitrogen and hydrogen electronegativity values, we would find that each of these bonds is polar and nitrogen is more electronegative. So each of those bonds has electrons moving more towards nitrogen because nitrogen likes electrons more than hydrogen. Now, they're all kind of pointing in the same general upward direction, and we don't have something up above. So, for example, we don't have another bond here that is going to cancel those other bonds. Instead, we have a lone pair at the top. So because electrons are all generally moving upwards in this molecule, we have an overall dipole moment for this molecule. So we could draw a big arrow off to the side showing that there's an overall movement of electrons going up. So that means that NH3 is a polar molecule. So let's practice. Let's see if we can determine if the following molecules are polar or non-polar. All right, so the first molecule is CH4, the second one is CH3Cl, and the third one is PCl3. So again, remember, we want to first draw the Lewis structure. And then second, we want to determine the shape of the molecule. And then three, we want to determine if we have an overall dipole moment. So pause the video, try this on your own first, and then we'll go over it together. All right, let's start with CH4. So let's draw the Lewis structure to help us figure out the shape of this molecule. So carbon is in the middle, it's by itself in the formula, but additionally it can make more bonds than hydrogen. So carbon again has 4 valence electrons. It's in group 4 of the periodic table. And each hydrogen has 1 valence electron. Okay, so this carbon has 4 bonded atoms. So what shape do we expect for this molecule? Tetrahedral. So this molecule actually looks like the following, where two of the hydrogens are in the plane of the paper, so those are the single lines, and then one hydrogen is coming out of the page towards us, which is represented by a wedge, and then the other hydrogen is going behind the plane of the page, so that's represented by a dash. Now, the main point here is that each of these hydrogens are equally spaced around that carbon, and the bond angle is 109.5 degrees for each of those hydrogens. All right, so let's determine the bond polarity for each carbon-hydrogen bond. So if we look up the electronegativity values for carbon and hydrogen, carbon has a value of 2.5, hydrogen has a value of 2.1. So the difference there is 0.4. So this is actually going to count as a non-polar bond, the carbon-hydrogen bond. So if each of the bonds around carbon are non-polar, then that means the molecule overall is non-polar. So each bond is non-polar. So the molecule is non-polar. Now, the other way to think about this is even if those bonds were polar, they're all equally spaced around the central atom. So that means that this would still be a non-polar molecule, even if each of those bonds were polar. So typically, if you have a tetrahedral molecule, it's going to be non-polar, as long as all the atoms are the same. Let's say we put in like one fluorine. That fluorine is super electronegative, so that would change things. That would make the molecule polar. And actually, we're going to see that in the next example with CH3Cl. Okay, so carbon again will go in the middle. It makes the most bonds, and it has 4 valence electrons. And then 3 of its bonds are to hydrogen, and 1 of its bonds is to chlorine, which has 7 valence electrons. All right, so again, carbon has 4 bonded atoms, so this will also be tetrahedral. So let's draw that tetrahedral shape. So we've got 2 lines, a wedge, and a dash. And one of those hydrogens, this is going to look similar to the molecule up above, but one of the hydrogens is a chlorine. You might hear my dog in the background. She's dreaming right now. She's making funny sounds. All right, so chlorine still has 3 lone pairs of electrons. Now, we said earlier that each carbon-hydrogen bond is non-polar, so those don't have individual dipole moments. But let's look at carbon and chlorine. So carbon has an electronegativity value of 2.5, and chlorine has a value of 3.0. So the difference is 0.5, which means that this bond is polar. So actually, electrons in this molecule are going to hang out with chlorine more often than carbon or any of the hydrogens. So this is going to give the molecule an overall dipole moment, which means that this molecule is polar. So we could also think about this in terms of symmetry. The molecule we looked at before, CH4, is symmetrical. Everything's evenly spaced, all the atoms are the same around carbon, but in CH3Cl, it's no longer symmetrical. We have that chlorine instead of a hydrogen. And that carbon-chlorine bond is polar. So that's going to make the overall molecule polar. All right, so let's look at our last molecule, PCl3. So phosphorus should be in the middle because it is by itself, but it also can make the most bonds. Chlorine can only make one bond. And then phosphorus is in group 5 of the periodic table, so it has 5 valence electrons, similar to nitrogen. And then each chlorine will have 7 valence electrons. So we'll just start pairing those up with phosphorus. Okay, so phosphorus has 3 bonded atoms and 1 lone pair of electrons. So the chart we saw in the last video would tell us that the shape for this molecule is trigonal pyramidal. So it's going to look like a little pyramid. So let's draw that. Let's draw phosphorus with one of its chlorines in the plane of the paper. One is going to come out towards us, so out of the page, and one's going behind the page of the paper. And then, of course, we have this lone pair of electrons up above, which I like to just draw as a little balloon up above. All right, so let's look at each individual bond. So between phosphorus and chlorine, phosphorus has an electronegativity value of 2.1. Chlorine has an electronegativity value of 3.0. So that gives us a difference of 0.9. So that is definitely going to be a polar bond. So for each phosphorus-chlorine bond, I'm going to draw little dipole arrows, and I want them pointing towards chlorine because chlorine is more electronegative than phosphorus. So it looks like overall electrons are kind of moving down and away from phosphorus and more towards each chlorine. So that means this has an overall dipole moment pointing down, and this is a polar molecule. So again, this will come up later and will be really important when we talk about whether molecules are attracted to each other or not. Now, one last thing we do need to cover is how to calculate molecular mass. So in the last chapter, when we talked about ionic compounds, we briefly looked at how to calculate ionic mass or ionic compound mass. But now let's talk about how to calculate molecular mass for molecules. Now, this is just going to be the sum of the masses of the atoms in the molecule. So it'll be really, really simple. Very similar to how we calculated the ionic compound masses. Now we do have to keep track of the number of atoms for each element in the formula. So for example, let's calculate the molecular mass of CH4. So we have one carbon, and its mass on the periodic table is 12.01 AMU. And remember, AMU stands for atomic mass units. And then we have 4 hydrogens. So that'll be 4 times 1.008 atomic mass units. And then we're just going to add all of those together. So if we plug that into our calculators, we should get 16.04 AMU. So super easy. It's going to be even easier because we don't have to deal with polyatomic ions and multiple polyatomic ions like we do with some ionic compounds. Okay, so now it's your turn. Pause the video and calculate the molecular mass of the following. All right, let's start with H2O. So we have 2 hydrogens, so I'm going to multiply the mass of hydrogen by 2. And then I'm going to add the mass of oxygen. And remember, on some periodic tables, oxygen is listed as 15.99 AMU. And then on other periodic tables, its mass is listed as 16. But either way, you should get a really similar value. So if we add those together, we get 18.02 atomic mass units, and that'll be the mass of water. Now let's look at the mass of C6H6. So we have 6 carbons, and the mass of carbon is 12.01 AMU, and we have 6 hydrogens. All right, so if we plug that into our calculator, we should get a value of 78.11 AMU. So super easy, not too bad. And we'll use these molecular masses later on when we start doing some calculations. All right, so we are done with chapter 4. And then in the next chapter, chapter 5, we're going to cover chemical reactions. So I will see you then.